plane is flying, which direction are we flying? East at 100 miles per hour, which is not very fast for a plane. That's okay. Maybe it's a small plane. The wind is blowing 20 miles per hour in the direction of 60 degrees north of east. What is the resulting speed and direction of the plane? So really what this question is asking us to do is asking us to add some vectors together. So here's how it looks graphically. The plane is going 100 miles per hour to the east. So we're going this way. And it doesn't look any different, right? But so our vector for the plane is 100 I, where the length of the vector is how fast the plane is going in miles per hour. Let me tilt this up just a little bit. And the wind is blowing at 60 degrees north of east. So it can always be kind of weird when people talk about how wind is blowing. They sometimes say it's coming from this direction, sometimes they say it's blowing in this direction. So they think it's blowing in the direction. So we're going this way. So 60 degrees north of east. Oops, that doesn't look like 60 degrees. That's 60 degrees north of east. 60, and that's a 20 mile per hour wind. So we need to find what that vector looks like. We know the plane's vector, or I should say the vector for the plane's speed or velocity is 100 I. And the velocity for the wind would be, well, we're going 20 in that direction. We need to figure out how much, we need the components is what I'm trying to say. So how do I want to draw this? Yeah, I'll just do it this way. It's just some trigonometry. So I want this component. So this component is going to be cosine of 60 degrees times 20. And this component is going to be sine of 60 degrees times 20. And this is 20. I suppose maybe I didn't fully explain what I was doing there. So maybe let me say that again in a less kind of assumptive way. Sorry. Sometimes I'm like, oh yeah, I know what the answer is. I think I need to let my cat out here one moment. So if we know this is 20 and we know that this angle is 60 degrees, if we call this component x and this component y, then cosine of 60 degrees is equal to x over 20, meaning x is going to be 20 times cosine of 60. And sine of 60 degrees is y over 20. So y is 20 times sine of 60 degrees. Sine of 60 degrees is root 3 over 2. So this is 20 times root 3 over 2, which is 10 root 3. And cosine of 60 is 1/2, so 20 times 1/2 is 10. So this vector here, its component form is, let's see, the x is 10, so 10I plus the y component is 10 root 3, so 10 root 3j. Sorry, one sec, let me let this cat out. Do you not actually want to go out? Oh, okay, you do. Good. Sorry about that. I'm trying to keep my door closed so my wife doesn't like overhear me just talking about Lamath stuff, but then sometimes the cats are in here and they're like, oh, we want to leave, or we want to stay. You know how cats are. Anyway, so if I want to find the direction that the plane is actually going in, it's going to be the wind vector added to the plane vector, or the speed of the wind, or the velocity of the wind added to the velocity of the plane. So we're just going to add the two things together. I think I can erase this now. So adding vectors component-wise is super easy. So if I want to find the plane vector plus the wind vector, that's just going to be 100i plus the wind was, sorry, I forgot, it was 10i plus 10 root 3j. So adding like components, that's going to be 110i plus 10 root 3j. That doesn't actually answer any of the questions though, because the questions were what's the direction and what's the speed. So the speed is the magnitude of this vector. So the magnitude of p plus w, well, we know how to find magnitude of a vector or length of a vector. Really, it's just the distance formula. You're taking, if you know that this is 110, and this is 10 root 3, you're doing the square root of this squared plus this squared, right? I'm just doing the square root of the I component squared plus the j component squared. That's kind of it. I can do this math. 110 squared is 121, sorry, 12,100. 10 root 3 squared is 100 times 3. So we've got the square root of 12,400, which is approximately 101.3. 111.3, sorry, miles per hour. So not a whole lot faster, right? Even though the wind is blowing at 20 miles per hour, only some of that is contributing to going in the direction the plane wants to go in, or I should say to pushing the plane further out from the way it's going. And then, or I should say, pushing the plane faster, right? If the plane is going 100 miles an hour this way, the wind is making it pick up another 10 miles an hour, even though the wind is blowing at 20 because they're not in the same direction. And then the direction is always kind of a weird question because, like, usually you're asking the direction compared to kind of what. So I'm usually thinking of the direction of east being the positive x-axis. And so we usually measure from the positive x-axis as being 0 degrees. So I'm asking, what angle are we looking at here? Well, my triangle, again, the x component is 110. The y component is 10 root 3. So if I'm looking at that bigger triangle, where this is my resulting vector, this is 110, this is 10 root 3. To find this angle, tangent of that angle equals 10 root 3 over 110. I could reduce that, I guess, to root 3 over 11. But to actually find tangent, we have to use a calculator. Or sorry, to find the angle, we have to use a calculator. Theta is going to be the inverse tangent of root 3 over 11, which is going to be, if we use a calculator, approximately 8.95 degrees, which seems not unreasonable, right? We were going completely straight east, and then we pushed it upwards a little bit. So we're not a full 60 degrees in the opposite direction because we still have a lot more velocity going eastward, but the wind is pushing us slightly off course. Questions about any of this? Yeah. You might say, like, I know in 21B, we didn't spend a whole lot of time talking about polar coordinates, but the idea here is very much related, right? If you've got some vector v emanating from the origin, there's kind of two different ways to describe the vector. If you're thinking about its coordinates in terms of x and y, this is x, this is y, and this is the point x comma y. One way to think of a vector v is x in the I direction plus y in the j direction. And that fully describes where it starts, where it ends. The other way to think about it, though, is to think about the magnitude which is another way of thinking about the radius, right? What we called it in polar coordinates, we call that part the r. Magnitude is just the square root of x squared plus y squared. And then the direction is the inverse tangent of y over x. So hopefully some of that looks vaguely familiar. We don't really memorize this, so we can always draw the picture and kind of figure it out. So let's get to talking about multiplying vectors. So there are two distinct and totally different ways to multiply. Well, actually, I guess I should say there are three ways to multiply vectors, really. So multiplying vectors. The first way is kind of lame. It's just scalar multiplication. So scalar multiplication just means you take a vector and you multiply it by a scalar. So scalar multiplication, right? If the vector v is something like, I don't know, 5i minus 12j, so it's going over 5 and down 12, right? Looks maybe something like over 5 down 12, looks kind of like that. There's my vector v. Then you can multiply v by, I don't know, like say 3. And 3v, you're literally just multiplying the components by 3. Not super exciting. 15i minus 36j. Okay. The magnitude would be 3 times as long. So I will point out that the magnitude of v here, sorry, the magnitude, we use those symbols if we can try it. The magnitude of v is going to be 13. Square root of 5 squared plus 12 squared is, square root of 5 squared plus negative 12 squared is the square root of 25 plus 144, which is 13. And the magnitude of 3v is just 3 times 13, which is 39. It makes sense. If you multiply the whole thing by 3, it's 3 times as long. So its magnitude should be 3 times as long. You could also do the math, though. You could see that that's going to be equal to the square root of 15 squared plus negative 36 squared. I don't want to do the math, but you can do the math. It's not terrible. But when we say how you multiply two vectors, or how you multiply vectors, what we really mean is multiplying a vector by a vector. And for vectors of any dimension, you can always find the dot product between them. So let's talk about the dot product. The dot product has many names. It's also called the inner product, or it's actually an example of an inner product. It's also called the Euclidean inner product, is actually the more specific name. So that's another name for the dot product. And there's a couple different ways to calculate it, actually. And we actually use both. Oh, man, I did something dumb. It's not super dumb, but it'll be dumb for the recording later. I forgot to pin my video, which means that example I just did will look super tiny. So I will have to try and I'll fix that later. Or maybe I won't. We'll see. Maybe that example won't make it to the video because I don't want me tiny. Then I don't think it shows your guys' pictures even or your names, but I'd rather not risk it. So I will cut that out if I need to. So the dot product, if you've got two vectors, so u and v, which have nothing in common necessarily, and there's an angle between them, then u dotted with v, one way to calculate it, the less intuitive way, or maybe the less easy way to calculate it, is to find the magnitude of u multiplied by the magnitude of v multiplied by cosine of the angle between them. And you might be thinking, well, okay, that's interesting, but so what so far? Let's look at some examples. Let's say our vectors were 2i and 3i. Notice that these vectors are in the same direction, right? Here's u. And I'm not going to draw them on top of each other because that feels kind of silly. Here's v. So in this case, we can totally calculate u dot v because it's easy to calculate the magnitudes. Right, this is just 2 in the x direction. This is just 3 in the x direction. So u dotted with v, the magnitude of u is just 2. And so if you have a vector, I mean, you can also calculate, right? The magnitude of u is the square root of 2 squared plus 0 squared. If a vector only has one component, the absolute value of that component is just the magnitude. So the magnitude of u is 2. The magnitude of v is 3. And cosine of the angle between them, well, the angle between them, if they're emanating from the same place and going in the same direction, right, the angle between them is 0. So that's going to be 6 times cosine of 0 is 1. So here, u dot v is equal to 6. Yeah. On the other hand, what if u and v are perpendicular to each other? So what if u is still equal to 2i, but now v is equal to 3j? So u looks like this, v looks like this. And the angle between them is 90 degrees. Well, now u dot v is equal to, still the magnitude of u is 2, the magnitude of v is 3, but the angle between them now is 90 degrees. And cosine of 90 degrees is 0. So that's going to be 2 times 3 times 0, which is 0. This actually leads us to an important statement, which is that two vectors are perpendicular, or more generally, orthogonal, if, it's actually if and only if, their dot product is 0. So in 2 and 3 dimensions, this is just the normal idea of perpendicularness, but we can also use this idea to define what it means for like the vectors in 4 or 5 or 6 dimensions to be perpendicular or orthogonal. So, and again, I know that's not the thrust of this class, but definitely in 22A, we do talk about higher dimension spaces and what it means for vectors that are 4-dimensional to be orthogonal. What does it mean? It means their dot product is 0. So let's look at another example. Yeah. And what do I really want to say here? I want to say something. So I'm trying to make sure I kind of tie everything in. Sure. So one way to calculate the dot product, well, actually, let me do this one more example before we talk about the other way, the easier way. So let's say we have this vector. We have u equal to 2i, and v is going to be 3i plus, I'm going to go a slightly different route here. Let's say it's 3i plus, excuse me, 6j. Okay, so I'm going to draw this. I can draw. Here's u, 2 in the I direction. I guess I could use like a coordinate system if you really wanted. All right, so I didn't make this tall enough, oh well. So over 3, up 6. And there's v. So u ends at 2, 0. V ends at 3, 6. And we can find the angle between them, specifically because I picked numbers that made the angle easy to calculate. You know, if you go over 3 and up 6, did I make it? No, I did not. I picked something dumb. Oh, not dumb, just not smart. I don't know what that angle is actually. It's okay. So here's my angle. And I'm going to say that u dot v is equal to, well, again, the magnitude of u is 2. Oh, I know why someone picked a different number. Oh, that's fine. Yeah. Okay, fine. I'm going to change it. Do you hate when teachers do that? I know I used to. Sorry, I thought I was picking numbers that made the angle 60 degrees, but I forgot I needed opposite over hypotenuse, not opposite over adjacent to be 1/2. So let's pick 3 and 4 because that's a little bit easier to find the magnitude. Okay. Sorry. Over 3, up 1, 2, 3, 4. There we go instead. So u dot v is going to be the magnitude of u times the magnitude of v times cosine of the angle between them. So let's see. Magnitude of u is still 2. The magnitude of v, well, if I go over 3 and up 4, right, then this triangle is a 3, 4, 5 triangle. So the magnitude of v is 5. Right, I've got 3, 4, 5. And although we could find this angle as the inverse tangent of 4/3, I'm just trying to find cosine of this angle. Well, that's easy enough. Cosine of this angle is 3/5. So I end up with 6. Okay, so here's the thing. Instead of doing this thing where we're drawing this triangle, you might notice that, yeah, actually, I might point out, in fact, that take a look at this. So cosine of theta times the magnitude of v here, well, that's just going to give me however long v is in the same direction as u. Let me say that again. Right, so if I'm looking at the magnitude of v, which in this particular example is 5, well, cosine of theta is equal to 3 divided by the magnitude of v. So cosine of theta times the magnitude of v is equal to 3 in this particular example. So the idea here is that if you're finding u dot v, you're basically multiplying the length of u times the length of v that is in the same direction as u. So if we think about it that way, well, clearly, since v is 3, 4, for this particular example, the amount of v that's in the same direction as u is 3. And so what we can say is that when you're trying to calculate u dot v, there is another way you can calculate it, which is you multiply the components of the same parts together and you add. So u dot v is going to be 2 times 3 plus 0 times 4, which is 6. So there's 2 ways of calculating the dot product between 2 vectors. You can either multiply the magnitudes together times cosine of the angle between them. It's not usually easy to find the angle between them. Or you can multiply their components together and then add up the results. So let me write this out. So let's say we have u, and you can write u as a vector in 2 or 3 dimensions. So let's say let's look in 3 dimensions. So let's say u is equal to u1i plus u2j plus u3k, and v also has 3 components. It's v1i plus v2j plus v3k. You can either find u dot v by doing the magnitude of u times the magnitude of v times cosine of the angle between them. And this gets to be a little messy, right? I mean, one, it's not usually easy, especially in 3 dimensions, more dimensions, to find the angle between 2 vectors. You could write more here. You could say, I will write a little bit more. This is the square root of u1 squared plus u2 squared plus u3 squared. And magnitude of v is the square root of v1 squared plus v2 squared plus v3 squared times cosine of theta. But the way most rational, normal people that don't want to break their brains, the way most people try to actually calculate the dot product is the following way. You just multiply the components together and add the results. It's going to be u1 v1 plus u2 v2 plus u3 v3. And the interesting thing here is that these are equal to each other. I will also point out that the dot, so clearly this way of calculating the dot product can be extended to any dimension, right? I wrote vectors that were 3-dimensional, but you could use any number of dimensions, right? 4, 5, 6, a million, whatever. It's also true for the dot product written this way, right? If u and v were 5-dimensional vectors, then u dot v would be u1 v1 plus u2 v2 plus u3 v3 plus u4 v4 plus u5 v5. Try saying that 4 times fast. You don't need to worry about those higher dimensions because that's not what this, right? This class is about actual like physical geometry stuff that makes sense in the real world with our brains. Right, the 4-dimensional stuff is okay. So we can use this to calculate all kinds of things. Like for example, if u is equal to say the vector 2i plus 5j, and v is equal to the vector, I don't know, 6i plus 3j. I'm going to draw this in a second. We can very, very easily find the dot product, right? The dot product, u dot v is equal to 2 times 6 plus 5 times 3, which is 12 plus 15, which is 27. Why does that matter? Well, basically, the dot product, and I know I said this before, but the dot product of two vectors is kind of the length of one vector times the amount of length the other vector has in the same direction. The other thing that's kind of neat about this is knowing this allows us to calculate the angle between any two vectors. So let's say I want to find the angle between these two vectors. I'm going to try and draw them here. Try and draw this somewhat nicely. 4, 5, 6. Okay, so I'm going to go 2i, 5j, so 2, 5. So there's my vector u over 2 up 5. V is over 6 up 3. And I'm interested in knowing what's the angle between those two vectors. It definitely is less than 90 degrees. It looks like the way I've drawn it, it could be in the realm of 45-ish degrees, but I don't actually know. But here's what we can do. We can say, well, I know that u dot v is 27, but I also know that u dot v is the magnitude of u times the magnitude of v times cosine of theta. So if I know u dot v is 27, and I know how to find the magnitude of u and the magnitude of v, I can solve for cosine. So what I can actually do is say that cosine of theta is equal to u dot v divided by the magnitude of u times the magnitude of v. This is the way I prefer to remember this formula. Most books will solve for theta and write it as theta equals the inverse cosine of u dot v over magnitude of u times magnitude of v. I don't think you need to do that. I would just remember this and then work with it when you need to. Something that is interesting about this is that since we know cosine is between -1 and 1, that means that the dot product of two things is always less than or equal to the product of their magnitudes, right? Because this can't be bigger than 1. Cosine theta can't equal something bigger than 1 or smaller than -1. So yeah, u dot v is actually less than or equal to the magnitude of u times I believe this is the Cauchy-Schwarz inequality, which comes up again in 22a. It's kind of it's a neat inequality. It's very much related to the triangle inequality. Not super important right now, but they are neat things. Anyway, let's find the angle between these two vectors. So I'm going to say that cosine theta is equal to u dot v, which is right there. And then let's find the magnitude of u and the magnitude of v. So the magnitude of u is going to be the square root of 2 squared plus 5 squared, which is 29. The magnitude of, sorry, I think I said v, I meant u. The magnitude of u is the square root of 29. The magnitude of v is the square root of 6 squared plus 3 squared, which is 36 plus 9 is 45. So then to find the angle, I would love to not erase any of this. I guess I'll erase this. And this is 2i plus 5j. This is 6i plus 3j. We can see that cosine of theta is going to be u dot v, which is 27, over u magnitude u times magnitude v, which is square root of 29 times the square root of 45. So then theta is going to equal the inverse cosine of this. Yeah, I'm going to simplify this just slightly. Square root of 45 is 3 root 5. 27 divided by 3 is 9. This is going to be 9 over the square root of 29 times the square root of 5. So let's see what that's going to be. You need a calculator here. So let's see, 29 times 5 is 145. The square root of 145 it's just tiny bigger than 12. So we're taking the inverse cosine of 9 over almost 12. So I'm taking the inverse cosine of 0.747 approximately. And I'm getting about, my answer's in radians, which is fine, 0.72 radians, but that I would prefer to have it in degrees, so I actually have an idea what that looks like, because 0.72 radians is not super meaningful to me at the moment. So let's see. Pi, where are you, pi? Sorry, I can't find pi. Class is over. I'm just kidding. Whoops. It's about 41.6 degrees. Which definitely seems plausible, right? It certainly looks like it could be about that because I actually drew it kind of nice. So this, pretty important, comes up quite a bit. Let's look at some more examples. Oh yeah. So 2 dimensions, not too hard. Or like if you really if you didn't have this formula, you could probably still figure it out by dropping a perpendicular from here to here and somehow figuring out how long this was and how long this was and using tangent or something. In 3 dimensions, it gets a bit more difficult to use the geometry skills we have. And so that's when you really want to just use, I mean, you want to use this anyway, but it becomes harder in more dimensions, in higher dimensions, I should say. Let's see what we've got here. So let's find the angle between the following 2 vectors. U is equal to 2i plus j minus 2k. And v is equal to 3i plus 4j. Sorry, 3i plus 4k. You don't have to draw these. I'm going to try and draw them for you so that you can see it. Again, my 3D drawing is, oh, darn, I forgot to look up for the 3D drawing things. I don't actually know if I have any, but I think I might, so I should actually remember to do that. I even wrote myself a note and then forgot to do it. Okay, so here's my x, y, and z axis. So let's try drawing v first because it's only got 2 components. So 3 in the x direction. Here's something I'll say about these. When you draw these kind of 3-dimensional coordinate systems, your y and your z marks should be the same length. So when I'm going 1, 2, 3, 4, 2, 3, 4, like those should be the same length. The x ones should be kind of a little bit longer, actually. Right? Longer or shorter? Shorter. Sorry, I mean shorter. Because, right, you've kind of taken these marks at their fullest distance apart from each other, and then you've kind of tilted it so it's more facing towards you. So the distance between them is going to look like it got a little bit smaller because of the perspective. So if I'm thinking of this as being a length of 1, I'm really just kind of thinking about where the circle going through that is going to hit the x-axis. So like these are where my marks are there. Hopefully that makes some sense what I'm saying. Okay, so I don't actually usually draw the circles, but that's what I'm thinking about when I'm trying to make the little marks on the x-axis. All right, so I'm going 3 in the x direction and 4 in the z direction. So I'm going to go up 4. So draw this parallel here. So that's my v. And again, so if I could actually draw this so the x was coming out towards you, it'd be coming out towards you, but up. So it'd be 3 in this direction, 4 in that direction. And then u is 2 in the x direction, 1 in the y direction. So let me use different colors. Colors are good. So there's 2i plus 1j, and I have to go down to yeah. Sorry, this is always complicated. Drawing just points in three-dimensional space is like not the easiest thing I've ever done in my life. But here's our vector coming kind of down and away and out towards us. So let me erase all this other mess that's kind of getting in the way of seeing things. So there's what we've got. We've got this vector that's going towards us to the left, to the right, I guess, and down. And this other vector that's coming towards us and up. And we're trying to find the angle between them. Okay, we never have to draw this, or we rarely ever have to draw this to actually be able to find the angle. The angle, super straightforward to find. We know that cosine theta is going to be u dot v divided by the magnitude of u times the magnitude of u. Cool. U dot v, 2 times 3 plus 1 times 0, because there's no j component here, plus negative 2 times 4 divided by the magnitude of u. Okay, the magnitude of u is the square root of, someone pick nice numbers here, 2 squared plus 1 squared plus negative 2 squared, which is 4 plus 1 plus 4, which is 9. Square root of 9 is 3. And the magnitude of v is 5. So I end up with, let's see, 6 plus 1 minus 8. So negative 2 over 15. So then theta is going to be the inverse cosine of negative 2 over 15. And here's something to know, right? If cosine is equal to a positive number, the angle is in the first quadrant, right? It's between 0 and 90 degrees. But if cosine is equal to a negative number, your angle should be in the second quadrant. It should be between 90 degrees and 180 degrees. So if you have cosine, or if you have inverse cosine of a negative number, you're going to have an obtuse angle. And that's going to be approximately, let's see, let's change the mode to degrees. So the inverse cosine of 2/15 is approximately 80. That doesn't seem right. Oh, I did 2/15, not negative 2/15. So 2/15, I got 80. So that's why it's good to know, right? To make a dumb mistake like I just made. Like, I shouldn't get 82 degrees. I just said it should be an obtuse angle. It should really be about 108 degrees. No, I think about 90 degrees. Let's check. So the inverse cosine of negative 2/15 is, that's, I don't have to use the calculator. I wrote cosine. Inverse cosine. One more time. Inverse cosine of negative 2/15 is 97.6 degrees. Yeah, so the supplementary angle to the 88. Supplementary? No, they're both different from 90 by the same amount. Yeah, so that does not mean supplementary. Sorry, one sec. Now I'm trying to make my brain see the same thing. No, those totally are supplementary angles. Yeah. Yeah, sorry. So this angle is approximately what I get here, 97.66 degrees. Which is obtuse. Okay, so I feel like there's, let's see, let me look at the next thing before I start saying stupid things. Yeah, I feel like there's more to say about the dot product before I get into the cross product. So again, I don't know how much your teachers are really going to say about this, but no. Oh, I know. Wait, just one sec. I'm getting ahead of myself. That's the problem. Yeah, no, I want to say this. Okay, so here's what I want to say. Yeah. So things to know about the dot product so far. So maybe three things so far. U dot V, you can either calculate as the magnitude of U times the magnitude of V times cosine of the angle between them, or you can calculate it as the components multiplied together added up. U1 V1 plus U2 V2 plus, right, whatever number of components you have. And then we have that cosine theta is equal to U dot V divided by the magnitude of U times the magnitude of V. And then finally, we also have that the dot product is equal to 0 if and only if U and V are orthogonal. There's the symbol for orthogonal or perpendicular. There are a couple other things that are worth mentioning, but they have to do with what's called the projection of U onto V. So let's talk about that for a hot minute. Let me draw 2 or 3 pictures here. So let's say here's V, and here's U. And we'll draw another picture as well. Here's V, and here's U. And the angle between them, let's say it's essentially the same. All right, so if I want to find what's called the projection of V, U onto V, which is often written this way, it's written as projection U and then a subscript V on projection. So projection subscript V U. This is the projection of U onto V. And it's exactly what it sounds like. It is you're literally dropping U onto V and saying what amount of U is on V. So I drop this down here. Let me grab a pen that's kind of trash. Yeah, you're kind of trash. Right there, that is the projection of U onto V. Whatever that vector is, that's what the projection of U onto V is. Same deal here, except here I have to actually extend V so I can see where U projected onto it lands. So even though V ends right here, this red vector, this is the projection of U onto V. So it's just the amount of U that is in the V direction. I will mention, because it's worthwhile, the projection of U onto V is not the same as the projection of V onto U. Right? If I dropped a perpendicular from V onto U, well, first of all, your direction would be different. You'd be in the direction of U. And second of all, the length would not be the same. So how do we calculate something like this? Well, it's just really like using some trigonometry. So if I want to find this here, it's going to be, well, let's see. I'm probably going to need cosine. So I'm going to say something about cosine theta. I'm really just actually kind of figuring it out. So cosine theta, it looks like cosine theta is equal to this divided by this. I should use magnitudes here because cosine is about length of things. So it's the magnitude of the projection of u onto v divided by the magnitude of u. Okay, we'll check out this magic. This wizardry. I'm going to multiply both sides by the magnitude of u. So the magnitude of u times cosine theta is equal to the magnitude of the projection of u onto v. And then I'm going to multiply both sides by the magnitude of v. Why? So that I can get the dot product showing up here. So oftentimes what we do when we're trying to like make something happen with all this kind of dot product weirdness or cross product weirdness later is we ask ourselves, are we dealing with cosine or sine? If we're dealing with cosine, then we're like, okay, I'm going to try and make the dot product show up. And then if we're dealing with sine, we'll see later we try and make the cross product show up. It's kind of neat. So I'm going to multiply both sides by the magnitude of v. So the magnitude of u times the magnitude of v times cosine theta equals the magnitude of v times the magnitude of the projection of u onto v. Well, look, that's just u dot v. So then, here's what we can say. We can say that, almost there, sorry. We can say that the magnitude of the projection of v, sorry, the magnitude of the projection of u onto v, apologies, is equal to the dot product divided by the magnitude of v. Okay, so why is this helpful? Well, here's the thing. We already know what the direction is, right? If you're projecting u onto v, it's in the direction of v. So when you talk about a vector, all you need to know is its length or magnitude and its direction. So the projection of u onto v. The magnitude is that. It's u dot v divided by however long v is. What's the direction? Well, you might say the direction is v, James. And I say, well, you're mostly right. Remember last time we talked about how when you're finding direction, you have to make it a unit vector, right? So because the idea here is I'm trying to actually find this vector here. Let's say, for example, no, let's actually finish this before I do an example. So the direction, well, the direction of v is just v divided by the magnitude of v. And that means the actual projection of u onto v is the magnitude times the direction. So the projection of u onto v is equal to this times this. U dot v divided by the magnitude of v times v divided by the magnitude of v. Okay, I want to point out, in this result here, only one thing is actually, I should say, how do I say this the right way? Everything is a scalar except for one thing. So u dot v is not a vector, it is a scalar, right? When you do the dot product of u and v, you get numbers plus numbers plus numbers, you get a number. Magnitude of a vector is also a number, magnitude of a vector is also a number. This is the vector here. So we often write the projection of u onto v as all the scalar stuff together. U dot v divided by the magnitude of v squared times the vector v. Okay, so let's actually calculate some things because I feel like this might seem very kind of like there's a lot going on here. But let's do some easy examples and then maybe some harder examples. I feel like I had some examples ready to go, but Maybe I hid them from myself. You know how I like to do that. No, that's not it. Maybe it's here. Sure, those are harder examples, but we can do those as well. That's not what I want to do. I want to do that. Okay. I will. So you might kind of think maybe I'm going in a weird direction here, but this is actually very important because when we talk about we talk about the projection not so much because we like the projection, because we actually are interested in this. Because what we're going to see later on, like in the section or two, is that if you're trying to find, like, say, the distance between a point and the line, what you're going to do is you're going to say, well, I can find the distance between a point and a line by finding the projection of the vector from a point on that line to this point, finding the projection, and then finding the orthogonal complement, and then finding the distance of the orthogonal complement. So it's kind of a lot of machinery building up to get to being able to find the distance between a point and a line, or a point and a plane. Kind of neat, kind of, I don't know. So let's say we have this very straightforward example. What's the projection of u equal to our favorite vector 3i plus 4j onto v equal to 6i. Okay, so let's draw it. Three I plus 4j looking like this. 6i looking like this. Okay, now I think everyone can see that in this example, if I'm going to find the projection, it's going to be just 3i, right? If I drop this vector onto v, the amount of u in the direction of v is just 3, because that's how much u is it, right? Because it's an easy direction. So I'm pretty sure we're still going to calculate it, but the projection of u onto v here is just the vector 3i. Let's go ahead and calculate. So I'm going to do the calculation kind of a long way. I'm going to calculate the magnitude and the direction separately. So the magnitude of the projection of u onto v is going to be u dot v divided by the magnitude of v. Okay, easy enough. U dot v divided by the magnitude of v is going to be, let's see, u dotted with v is going to be 3 times 6 plus 4 times 0. The magnitude of v is going to be the square root of 6 squared plus 0 squared. So we're going to get 3 times 6, which is 18, divided by 6, which is 3. No surprise, right? We knew, or we were pretty sure that this was going to be our resulting vector, which definitely has a magnitude of 3. Okay. What's the direction of v? Well, the direction is, the direction of the projection, which is in the same direction of v. So the direction of v, so here's the thing, you can't just say the direction of v is v. I know that seems dumb, but it is what it is. So if v is equal to 6i, the direction of v is v divided by its own magnitude, which is 6i divided by 6, which is just I. So it's a vector in the same direction. It's just a unit vector, or a vector of length 1. I don't want to ruin my blue pen. So there is your v divided by the magnitude of v. And then to get the actual projection, you take your magnitude times your vector direction, and that's it. So the projection here is 3 times I, which is 3i. Now, no one in their right mind is actually ever doing this separately. You're not saying, what's the magnitude? What's the projection? You're doing it all at once. So the way we would actually calculate this is you would do the projection of u onto v is going to be u dot v over the magnitude of v squared times v. U dot v we saw was 3. Sorry, u dot v was 18, apologize. Apologies. Magnitude of v squared is 36, and v is 6i. So 1/2 of 6i is certainly 3i. Cool, so it works. So that's how you calculate the projection. And then if you want to know what the orthogonal complement is, well, here's what's true. Let me go to the other side here. So if I want to find u is going to equal the projection of u onto v plus the orthogonal complement. I don't know if there's good notation for the orthogonal complement. Let me look in the book here real quick. Sometimes people make up nice notations for it. Sometimes people do not. I'm not seeing particularly nice notation here, which is typical. Sorry, I just want to double check. Yeah. So I'm going to call this the orthogonal complement for a second. So here's the projection in red, and from the end of the projection to the end of u, there is your orthogonal complement. So the projection plus the complement is equal to u. So the way we calculate the orthogonal complement is u minus the projection of u onto v. So in this particular example, the orthogonal complement is u, which is 3i plus 4j, minus the projection, which is 3i. So the orthogonal complement is just u minus the projection of u onto v, which is 3i plus 4j minus 3i, which is equal to 4j. No big surprise there, right? Because to get from here up to here, you're just going 4 in the y or the j direction. Yeah, so again, right, if I was trying to find the distance between this point and this line, I would be finding the length of the orthogonal complement. And that's eventually where we're going to go with this. I feel like there was something else I had to say here. Maybe not. Oh, I know what it was. So one way that you might see this occasionally written, just so you're aware, is that either way is fine. So the projection of u onto v is either written as u dot v over the magnitude of v squared times v, and that's the scalar. That's the scalar. But some people also like to write it as the following. U dot v divided by v dot v over times v. Because it is actually true that the magnitude of v squared is equal to v dot v. Let's check that out. So the magnitude of v squared, well, the magnitude of v is the square root of the components squared added together. Let's say it's 3-dimensional. So the magnitude of v is v1 squared to v1 squared plus v2 squared plus v3 squared. And then if I square that, I just get v1 squared plus v2 squared plus v3 squared. But if v is equal to, right, v1i plus v2j plus v3k, if you dot something with itself, it's the I components multiplied together, so v1 times v1, plus the j components multiplied together, v2 times v2, plus the k components multiplied together, v3 times v3. So the magnitude squared is the same as the vector dotted with itself. So people write it like this, people write it like this. Let's do a slightly harder example. Let's look at the, I see Grant has some notation. Oh, that's interesting. I don't see that notation in the book, but that is okay. I will use that notation because it seems like good notation to me. I'll tell you what it is in just a second. So let's look at these two vectors and find all the things. So let's say my vectors are u equal to 3i minus j plus 5k. So we're in 3 dimensions. And v is 2i plus j plus 2k. And let us find the following. So let's find the projection of u onto v. Okay, and maybe we'll actually, yeah, let's start there. So the projection of u onto v, you're not deriving the formula every time, right? Eventually you're gonna be like, okay, I've memorized this formula. Projection of u onto v is u dot v divided by v dot v times v. Right? If you're projecting onto v, you should be in the direction of v. That's how I remember which one ends up over here and down here. Okay, that's not too terrible to calculate. That's going to be, let's see, u dot v is 3 times 2 plus negative 1 times 1 plus 5 times 2. So 3 times 2 plus negative 1 times 1 plus 5 times 2. V dot v is going to be 2 squared plus 1 squared plus 2 squared. And v is the vector 2i plus j plus 2k. So calculating this, we get, let's see, 6 minus 1 is 5 plus 10 is 15 over 2 plus 1 plus 2 is 9 times 2i plus j plus 2k. So let's see, 15 ninths reduces to 5 thirds. So you get 5 thirds times 2 is 10 thirds I plus 5 thirds j plus 10 thirds k. So that's the projection of u onto v, and not surprisingly, it's in the same direction as v, right? Projection of u onto v is just a multiple of v, right? It's 15 ninths times v, and they are in the same direction. That's why my nose really itches. All right. Okay. How do I find the orthogonal complement? So here's the notation that Grant has used, which I think is perfectly good. The orthogonal complement is the complement of u onto v. So the orthogonal complement of u onto v is just u minus the projection. So, okay, well, we can do that. That's going to be 3i minus j plus 5k minus all that. 10 thirds I plus 5 thirds j plus 10 thirds k. So let's see, this is 9 thirds minus 10 thirds is negative 1 third I minus 1 minus 5 thirds and minus 3 thirds minus 5 thirds is minus 8 thirds j, and 15 thirds minus 10 thirds is 5 thirds k. And it's called the orthogonal complement for a reason. It is orthogonal to the projection. So this complement and this projection are orthogonal to each other. Meaning if we take the dot product, it should be 0. And it is. Let's take the dot product. So if we dot this with this, I'm going to get negative 1 third times 10 thirds, which is negative 10 ninths. I'm going to get negative 8 thirds times 5 thirds, which is negative 40 ninths. And we get 5 thirds times 10 thirds, which is 50 ninths. Oh yeah, that's 0. So, I mean, they are orthogonal. Ah, darn it, stupid pen on my thumb. Let's see, what else do I want to say here? Yeah, I guess we can go ahead and, I think it's, oh no, I know. There was so I did see a kind of a cool problem I thought was kind of fun. Let's take a look at this problem, which I think is neat. You might disagree. That's okay. You're welcome to your opinion. So angles between things in 3 dimensions, I think, can be quite difficult to visualize and or find. Maybe the visualizing more so than the finding. So here is a question that I think is interesting, especially if you like chemistry, physics, whatever. Molecules. I mean, I think we all like molecules. They're kind of what keeps us together. Find the bond angle between the carbon and one seems like the wrong word, but whatever. And one of the hydrogen atoms. I feel like you really need 2 here, but whatever. On a methane molecule, CH4. And that's probably not super helpful if you are like me and you don't know much about how molecules look. It's a tetrahedron with the carbon in the center. So it's a tetrahedron with carbon in the middle, or center. So when I first saw this problem, I visualized it like this. I got my tetrahedron, which you need an equilateral triangle, and then boom, you like connect all the things. And then there's a carbon like in the middle. And drawing it that way is not the most helpful way to kind of think about where things live. So here's actually the useful way of drawing or thinking about where the tetrahedron is. So I'm going to draw it like this. I'm going to draw, actually, let's just be super smart about this, James. I didn't give myself enough room to be smarter than that. Sure. So let's do it like this. So if you think about it, a tetrahedron can be thought of connecting some of the corners of a cube. Specifically, corners that are like opposed from each other. So basically, if I connect, and I'm going to do it this way, I always end up blowing this. Let's see. So first of all, not those corners. Good job, James. These corners and these corners. So if I connect all of these corners to each other, I'll have a tetrahedron. Like, really? Really? Kind of cool. Oh yeah, it's kind of cool. So I'm trying to find, and then there's a carbon at the center. And now here's the thing. If I think of this point here as the origin, so here's my x-axis coming out this way. Here's my y-axis coming out this way. Here's my z-axis coming out this way. And I think of this as a cube where all the side lengths are length 1. So this is the point 1, 1, 0. This is the point 0, 1, 1. This is the point 1, 0, 1. Well, if a carbon is in the center, it's at the point 1/2, 1/2, 1/2, right? The center of, and that, so I know like my picture is a little bit hard to maybe see everything. I feel like you can see it all right. It's got one. I feel like I've drawn too many lines. Did I draw too many lines? No, I'm just so not used to this orientation of the tetrahedron. That's why. But no, that's right. Like you got your triangle, and that's okay. Okay. So anyway, the center of the tetrahedron is the same as the center of the square. It's 1/2, 1/2, 1/2. So I'm trying to find the angle between. Let's make easy choices. I'm trying to find this angle. Right, there's my carbon, and there's my hydrogens. I feel like one hydrogen is not, again, not the right word. But I'm trying to find, like, if I go from one hydrogen to the carbon to another hydrogen, it should be the same angle no matter which of them I pick because of the symmetry. So I'm going to try and find that angle. And the way I'm going to find that angle was by making a less complicated picture. So I'm thinking, all right, I've got this kind of deal. I'm going up to this point here. 1 half, 1 half, 1 half, and then back down to this point over here, which is 1, 1, 0. Okay, so I have to think about how to describe each of these vectors. So the vector that starts here and ends here. So the way you find the vector, if you know a starting and ending point, is you do the ending point minus the starting point. So this vector, which let's call this one V, the vector V is 1 minus 1 half, 1 minus 1 half, 0 minus 1 half. And U, which starts here and ends at 0, 0, 0, maybe I should have done those the opposite way, but that's going to be negative 1 half, negative 1 half, negative 1 half. Also, if I thought about this maybe a little bit more, I might have made all the side lengths 2, so that these things were all 1, 1, and negative 1, and 1, 1, or negative 1, negative 1, negative 1. That might have been a little easier. It'll probably be fine. So then we can find the angle between them, right? Cosine of the angle between these two vectors is u dot v divided by the magnitude of u times the magnitude of v. Yeah, I really do want to make it kind of, so yeah, here's the thing about, can I say that? Yeah. If I scale these both by the same amount, the angle between them will still be the same, right? If I make this vector twice as long and this vector twice as long, then you'll still have the same symmetry. I feel like that's safe, but now I'm worried it might not be safe. All right, so I'll just use these numbers. So u dot v is negative 1/4, negative 1/4, positive 1/4. So that's going to be negative 1/4, I think, yeah. The magnitude of u is the square root of 1/4 plus 1/4 plus 1/4, so the square root of 3/4. U and v should have the same magnitude, right? They're both the distance from the center to one of the ends. So if the magnitude of u is the square root of 3/4, the magnitude of v is also the square root of 3/4. So we have negative 1/4 over 3/4, which is negative 1/3. Which means our angle is going to be obtuse, which is certainly how it looks. Maybe, I don't know. So theta is the inverse cosine of negative 1/3, which if you bust out a calculator, is approximately 109.5 degrees. So that's kind of neat, right? If you take a tetrahedron and then some point in the center, the angle between any two vertices in the center is going to be 109 degrees-ish. Cool.